Start with a blank square. Divide it into 9 smaller squares and make the center square red. For the remaining 8 squares, do the same thing. Divide them into 9 smaller ones and make the center red. Now each side square looks like the first one after its center was made red, so for each of those, let's repeat the process. And repeat it again and again, an infinite number of times, making smaller and smaller red squares each time. On any given step, there are more white squares than red squares, so if we zoom back out and look at the whole thing at the end, what will it look like? Will it look pretty much like the first few steps, but with a few microscopic red dots? Will the whole thing eventually turn red, or will it form a fractal? Well, if you'd like to know the answer, just keep watching this video. To start to explain the pattern, let's look at how much of the original square is turning red. So we started by dividing into 9 smaller squares and then making the center red. So this means that 1/9 of the original square has turned red after the first step. Next we divided all the other ninths that aren't red into their own smaller ninths. So 1/9 divided by 9 is an 81st, so 1/81. And each of these new smaller squares are an 81st of the original square, and we make 8 of those red, so all the center ones. So now we have a 9th plus 8/81 as the ratio of the original square that has turned red. Next, let's zoom in on one of these outside squares. So we take the side 81sts and divide it by 9 again. So 81 times 9 is 729, and we now have 8 more of those tiny red squares that are a 729th of the original. But hang on, we also do this for all the other side squares, so we'll multiply that whole thing by 8 to get the actual ratio for this third step. And so there should be enough steps here to actually notice a pattern, and let's go ahead and have a closer look at these numbers. Now what we want to do is find the bare bones description for these numbers we came up with, and that way we can predict what the 4th step will be, or the 5th step, or the infinite step. And so let's dissect what we have here. Each iteration, we multiply the numerator by 8 and the denominator by 9. And we're adding each of these numbers up. So we want another way to write this. The first one is just 1/9. We don't need to multiply or divide anything else. So let's go ahead and include that 8/9 we just talked about, but it's to the power of 0. So that should just leave 1/9 for that one. The second number is multiplied by 8 and divided by 9 once. So let's put that fraction 8/9 to the power of 1. And for the third number, we need to multiply by that fraction twice. So let's have a power of 2. So here's what the series looks like with our new way of writing it. And it actually gets even more simple if we use a summation sign, and that looks like this. So all this is saying is go through and add up each number that the formula spits out from n is equal to 1 all the way up to infinity. And once all those ratios are added, that will tell us what ratio of the original square has now become red. Now if we replace our numbers with symbolic variables, really what we have here is a geometric series. And that's the name for what you see on the bottom there. And for some cases of this series, it can result in a finite number even though you're adding infinitely. And for our problem, that finite number would actually be the fraction of the original square that's turned red after infinite repetitions. And so what I'll do next is show how to find that number And it is a lot of math, so if you'd like to just see the final equation, I'll have a timestamp in the description. Let's make a new variable for the result of the geometric series, called s sub n. If we write out the terms in our series, it should look like this. And something interesting we can do here is multiply the result by r, and this will also multiply all the terms in the series by r. And with how exponents work, this will just add 1 to every exponent that's over an r, and we can compare this with the original series. They have a lot of similar terms, and so we can take the difference between the two. All the identical terms from each series will cancel, leaving only a few terms left. Here's all that we're left with after the subtraction, and we can do some algebra. We can pull out the s sub n that's on the left side, and then divide what's in the parentheses over to the right side. And this is what our series is equal to. Notice the r to the n. Now if r is just a whole number and n goes to infinity, then it's going to get really, really big. However, if r is a fraction less than 1, then it's actually going to get smaller and smaller and eventually disappear. So we can drop that part for the particular case that r is between -1 and 1. If we rearrange a little bit, then we find our answer. So if r is a fraction less than 1, then an infinite geometric series is equal to this arrangement of variables right here. Now let's apply this to the pattern we came up with for the red squares. Plug in 1/9 up top for a and 8/9 for r on the bottom there. Subtracting 8/9 from 1 leaves a 9th on the bottom, so this is equal to 1. This means that after infinite steps of the pattern, the fraction of the original blank white square that becomes red is 1. In other words, for the one original white square, we're left with one new red square. We have our answer. The whole thing will eventually turn red. Alright, thanks for watching. I hope this little problem piqued your interest. I thought it was a pretty neat extra credit problem I did for my Calculus 2 class. And really my goals for this channel are to share things I've worked on, but also to offer some exercise for my brain and the brains of viewers like you. I think that form of entertainment can be kind of a breath of fresh air amidst the majority of what the internet throws at us nowadays. So if you're not already, maybe consider subscribing, and I'll see you in the next one.